All right, let's continue our study of current and forces, magnetic forces, and that kind of thing. We're picking up with 30.5 where it says induction and energy transfer. We have motional EMF. So now we have electromotive force. We have electrons, things that are moving, and that's producing an electric force or an electric field, a potential difference. And so what we've got here is a bar, right, or something, some type of rod, and it's moving in a magnetic field. So I'm going to put a B here so we see that. And it's moving this way. So we'll make that the velocity. And it has a length right from here to here. Okay, as it's moving this way, what's happening? It's moving this way. That means that if there are any, or the positive forces, right, the positive charges rather, QV cross B, positive forces are going to get pushed this way, and negative forces are going to get pushed that way. So I've got positive and minus, positive collecting here, minus collecting there. And now I have an induced EMF, okay? And so the question is, you know, what is the direction on the positive charge? Up. What is the direction on the negative charge? Down. So which end has a higher potential? The potential of C is greater than the potential of D. This is a positive, that's a negative potential. And so what is the direction of the E field? E field points from negative to positive. So the E field points down from C to D. Okay. So let's take a look here at what's happening. And so we've got, if this thing is moving through here, what will happen? The forces will balance, right? More force, less force, until the point where, right? These are going to separate until the point where the magnetic force is equal to the electric force, the electric field force. And so again, we've got QVB sine theta equals QE, but theta is equal to 90, so sine theta is 1. And so VB equals E. And so potential difference, V, is ED, but E, like we just solved, is VB. Right? So this is velocity times the magnetic field. And D. Whereas D is the distance, right? The length, rather, of this thing. And so the EMF is going to be d phi dt. But what is it that's changing here? So this is b dA dt, but because the magnetic field is not changing, the angle is not changing, so it's not the cosine theta in b dot A. But the area is changing. How is the area changing? Well, it's b times L times L. And then we've got this thing is moving. What's in here? Let me just make sure I get that right. L, and then the velocity. So then I've got dx dt, and that's the velocity. So it's b L v. Right, so that's the induced EMF, BLV in this case. The current then is going to be this divided by R, if there can be a current. Right. And we will see examples where there is a current. And then the power is going to be the EMF squared divided by the resistance. So let's take a look at example 10. This actually happens, right, where we have something moving through a magnetic field because the Earth has a magnetic field. And so even an airplane traveling through, there's a magnetic field. We want to know the potential difference between the wingtips based on this information, okay? So we assume the wingtips have a length of 30 meters, and it's moving 800 kilometers per hour. Convert that, and I believe you get 222.2 meters per second, so that's our velocity. And we want to know the magnetic field. So realize here the vertical component of the magnetic field is 1 times 10 to the negative 4th Tesla. And so, right, so we got to calculate and get the vertical component is there at a declination of 60 degrees. And so that it looks like this here's the magnetic field. We've got the horizontal and the vertical components. And this one is 1.2 times 10 to the negative fourth. And so, let's see, this is equal to B sine of 60. All right. And so then when I calculate the EMF, potential difference from one wingtip to the next, it's B LV sine of theta. All right. But again, so this is B sine of theta times LV, and this turns out to be 0.8 volts. So we want to know a general expression for the induced EMF of the bar. And so in this case, EMF is BLV sine of theta, but in this case, sine of theta is 1, so it's just BLV. And then we want to know the magnitude and direction of the current through the resistor. Okay, so this is for part B, I is going to be E over R or BLV over R, just like what we had before. But we want to know the direction here as well. And the current, I think, is indicated there on the thing. But just so you can see, so it's QVB this way. So that means that kind of from our perspective, it's going to be going around counterclockwise. So that, in the same direction that they indicate there, kind of down and to the left is the direction of the current through the resistor. And then the power, again, P equals V squared over R. So this is BLV, this whole thing squared over R. That's the power delivered by the applied force. Okay, example 12. So this one's a little different. Due to an applied force, a conducting bar of length L and mass m glides along two frictionless conducting rails. An applied force gives the bar initial velocity v naught, and the applied force is then removed and the bar continues to move to the right. Find expressions for the following as functions of time. Okay, this problem is pretty involved, and I have seen some AP problems like this. Usually the level 3 problem on the AP exam is where it shows up, if it shows up, not all the time, but I have seen it before. So the first thing to kind of keep in mind here, let's imagine this thing, right? Here's the magnetic field, and we've got some circuit thing here. Here's the resistor and these rails, and then here's the bar. The bar is moving this way, so this is V naught. So what direction is the force? QV cross B. If it's moving this way, it has current this way. But the current is going this way, so now there's another force on it, right? Current in, right, IL cross B. Now there's a force this way, FB. And FB is given by IL cross B, right? And so, and we know that F equals MA. And so, let's see. And the current is given by BLV over R, like we saw from the last one. Okay, so we've got MA equals BLV over R. And now times L and times B. So it's going to be, and A is dV dt, right? So we've got M dV dt is V B squared L squared over R. Okay. And this is negative 2 because this force is in the opposite direction it's going, so we can toss a negative on there. So what are we looking at here? Right, we want an expression for the velocity of the bar as a function of time, and so what we're going to end up having to do here is solve for v. But we see we've got dv dt in here, and this is going to be a little tough, but familiar to you at the same time. All right, so let's go over here, give ourselves some more space, and so I'm going to have 1 over v dv dt. equals m b squared L squared over r. That's it, right? So now I take the integral of both sides, and I'm looking for v as a function of time, right? So this is going to be from v naught to v for 1 over v dv dt. I'm starting with v naught, and then I'm going to integrate from time 0 to some later time t, m b squared L squared over r dt. All right, so this ends up becoming natural log of v over v naught, right, equals, this now is just m b squared L squared over r times t. So take everything to the power of so we can make this, oh yeah, so v over v naught is e to the m b squared L squared over r times t. So v is equal to v naught e m b squared L squared over r times t. And so that's it. I mean, that's our expression. Nice, simple problem, right? But I mean, if you know the process and what you're going for here, then it really is kind of simple. Except that I forgot the negative signs here, and so it looks like that. So as time goes on, the velocity is getting smaller. What's the other thing we're looking for here? Oh, the induced EMF. Well, you know, the EMF is just BLV, and so EMF is BL, and then V is a function of time. So you just plug this function into that. I don't feel like writing the whole thing out right now. And then the other thing you're looking for is the current. Current is just this divided by time, right? So I, and I is changing, is going to be the EMF over R, whatever the resistance is in this resistor. Okay, and so that's example 12. Might take up more space than what you need, or what you have there. Should have told you that before. Okay, the next thing, 35, alternate derivation for power. That's enrichment. You don't necessarily need to know that. Eddy currents. Ask me in class, and I'm going to show you a demonstration of this. But the idea is that as you're moving something through a magnetic field, a conductor through a magnetic field, it produces a current in the conductor, and it actually produces a force backwards. So as you're pulling the thing out of the magnetic field, you'd actually feel a force back. And we can do this by taking a really strong magnet and putting it on an aluminum track. Aluminum, because aluminum is not ferromagnetic, it's not going to stick to the track, but it will produce a field. And as the magnet slides down the ramp, it produces a force back on the magnet as eddy currents are created in the aluminum track, which we have here in the room. Okay, induced electric fields, and so as a result, right, if you have you know, something like a ring, and you increase the magnetic field, then you're going to get an induced current. And if you have an induced current, then you have an induced electric field in order for the electrons to move. And so a lot of this is, I would say, enrichment as well. You're not going to see a lot of examples like this. But if you consider the circular path of radius r in a uniform field, the field is increasing, and if we take out the ring, now you can see the path of the current, but it's an abstract line. And the EMF along the path is E dot ds, right? So you're adding that up. And then the induced field is negative d phi dt. And so the main point here is that what you're producing is an electric field, and then you've got your own magnetic field being produced, or here's how you get the electric field as a result of the changing magnetic field. And so what we're going to, and so if you have, current going through something like a ring, now you've got a potential difference on either side of that ring coming into and coming out of it. And that's going to come into play with 30.7 inductors and inductance. Whereas when dealing with capacitors, the energy was stored in the electric field. Now the energy is stored in a magnetic field because an inductor is basically a solenoid. And so the symbol, it looks a little funny there, but the symbol for a solenoid in a circuit looks like that. Remember, so this is a resistor, right? Those are jagged lines. This is a capacitor, right? Capacitor, resistor, inductor. And the key thing here is that, here I have charge collecting, so static charge. Here I have charge moving through, so I have current. And here the thing that induces the magnetic field is a change in the current. And so this is Q, this is I, and this is di dt. That's an inductor. And inductors are measured in, do I tell you here? They're measured in henries. So use capital H to measure inductance, and we use L as the symbol for inductance. Okay. And the geometry, the formula that tells us inductance, I call this one the Luna equation. L is mu naught n squared A over L, where n is the number of loops, mu naught is the permeability of free space, A is the cross-sectional area of the inductor, and L is the length of the inductor. Okay. And so we're thinking back to other stuff we've looked at in this unit from Faraday's law for coil of n turns, what the EMF, the induced EMF is. And it turns out the induced EMF is negative L di dt, okay? Because the induced EMF opposes the change in current. Remember we said that the induced current opposes the change in the magnetic field? Well, here we have, if the current is decreasing, then I have a change in magnetic field. And so I'm going to induce a change in the opposite direction. So it's kind of like a self-induced magnetic field that's being created. Okay, and so here's an example. Let's take a look at example 13. So delta I, the change in current over the change in time, it's a constant. Change is 1 amp minus 5 amps in 0.1 seconds. So that's negative 40 amps per second. All right, well, the induced EMF is negative L di dt. This is di dt. So that means that L is negative EMF over di dt. So this is going to be 2 volts over negative 40 amps per second. That comes out to 0.05 henries. Okay. Again, the geometric considerations of a solenoid, these are different ways of looking at what the inductance is. Again, the most popular is what I call the Luna equation, Lunal. It's got the L at the end. So if that helps you remember, great. So for capacitors, it was seed, the seed equation. For resistors, it was Rolla. And for inductors, it's the Lunal equation. As strange as that sounds. Example 14. All right, something similar here. So they give us some information, and we can find what the inductance is, mu naught n squared. Don't forget the n squared. I don't know how to get the squared into the Lunal thing, whatever you call it. And so this is, 4 pi times 10 to the negative 7th, like we've said before. This is 500, it's a 500 turn solenoid. This is 0.002. That's the cross-sectional area. And the length is 0.05. And you should end up with 0.013 henries when you do that. Example 15, this here is asking for the number of turns based on giving you the inductance, and all the other stuff. And so if I take this equation and I solve for n, then I end up with L times L over mu naught A and the square root. That's the number of turns. And so L, the inductance, is 0.178. This is 0.2. Mu naught is what it usually is, 4 pi times 10 to the negative 7th. And then 0.01 is the cross-sectional area, which you have to calculate based on the diameter. Don't forget that's the diameter, so 0.1 centimeter is the radius. And you should end up with 300 turns, which we leave as unitless, but you can say turns if you want there. Okay, so if you have a dielectric placed in a capacitor, you can do a similar thing with inductors, right? You can place some ferromagnetic material inside the inductor, and that changes the inductance. You're not going to see a whole lot of that, but you will see some. Here's an example. You have an inductor. It's around an iron ring, and so here instead of mu naught, the permeability constant, we would use 400, right? 400 times the mu naught thing, and it works the same kind of way, right? L equals this constant. We don't really have a thing. You just use kappa if you want. Mu naught n squared A over L, right? And it's a toroidal coil. So the information, this is 4 pi times 10 to the negative 7th, and the number of turns is 1,000. This is 1 times 10 to the negative 4th, right? And L, the length is pi times 0.05, because it's the circumference, I guess you could say, or the length, the internal length of that ring. Okay. So this ends up being 0.32 henries. So this would look something like this, if this helps. You've got a wire coming in, and it wraps around. Something like that, right? Wraps around the whole thing. Obviously, that's not 1,000 times, but you get the idea. Okay, now self-induction. This is like what we were saying before about having, a potential difference. You've got current going through a wire, through an inductor. If the current starts to go down, then what you have is a change in current. If you have a change in current, you have an induced EMF. If the current is getting smaller, then you have a changing magnetic field. So imagine, let's do it this way. You've got some coil, or not coil, solenoid, kind of like this. All right. And because it has current going through it, it has a magnetic field, right? If the current is going this way around it, then it's got a magnetic field in here that points that way. If the current starts to decrease, this magnetic field is going to start to decrease. But if you have a decreasing magnetic field, that induces current, right? That induces an EMF, and it's going to induce an EMF to oppose that, so in the opposite direction. So what you end up with is this creating resistance as long as the current is decreasing. This is kind of like a capacitor in the sense that when there is a constant current through it, it doesn't have any EMF, right? So after a long time, it acts like a wire. But at first, when this thing is charging up, but what's charging up here is the magnetic field. Then it will be producing some resistance, but it's resistance in the form of EMF. And so the potential difference from one end to the next is L negative L di dt, because it's pointing in the opposite direction that the current is changing. All right, so if we're thinking about capacitors, right, think back now to unit 8 that was. On a capacitor, the charge on the capacitor goes like that. Right, if this is Q and this is T. And dQ dt, which is the current, right, was doing this. The current was going down as charge was collecting on the capacitor. But if you have an RL circuit, right, so we had capacitor circuits, we have resistor circuits, now we have an RL circuit, so it's a resistor and an inductor together, then it's something different, right? This is charge collecting. So what's going to happen in this case, we've got, given enough time, the maximum current will be the EMF over R, right? Where this is the whatever other resistors there are in the circuit, because after a long time, the inductor acts like a wire. Okay, and so this is I max, and this is the current through the inductor. All right. So I'm going to write IL. That's the current through the inductor. This then is di dt. Okay, and this is starting off with EMF over L, because E is L, ut. Really, this should be negative. So if I solve for the initial di dt, that's the potential difference across the whole thing is the potential difference on the battery divided by the inductance. Okay. And so now we have a new time constant as well. Just like in RC circuits, it was RC. So now tau is L over R. And these are exponential equations just like we've had before, right? The some constant times 1 minus e to the negative t over tau, or some constant times e to the negative t over tau, where that initial thing times the exponential is this, right? Whatever these either start or asymptotal values are. Right, so then if I have an inductor that is charging, I equals EMF over the resistance, 1 minus e to the negative t over tau L. Right. This is the current for a charging RL circuit. Okay. And if it's discharging, so the same thing can happen also, right? Where I take out the battery and then I connect it, so now it can discharge. In a discharging inductor, the current is EMF over R times e to the negative t over tau L. Okay. So let's take a look at example 18. So for part A, di dt is going to be the EMF over L, so that's 12 volts over 0.1 henries. That gives you 120 amps per second. Okay, B, what happens to di dt? Well, di dt goes to 0 over time. As time goes to infinity. And then the current at time equals infinity will be I max. Right, so that's going to be just EMF over R. So that's 12 volts over 20 ohms and 0.6 amps. Part D looks like this. Here's the current, here's the time. The current is increasing over time, and it's at the time constant, right, L over R, or we want to know what's the time required to reach 63%. Well, one time constant is 63%. So, I mean, you can do this where you write out the whole equation, but you don't have to. If you know one time constant is 63%, then all you have to do is calculate the time constant. So R over L, R is 0.1, and, L over R. We'll try that again. So this is 0.1, and this is 20, all right, henries and ohms. And so you get about 0.005 seconds, or 5 milliseconds. Okay, combinations of inductors. In series, you add them up. In parallel, it's the 1 over rule. So inductors are like resistors. Since capacitors are like springs, we needed a pair for resistors. And so it was nice of nature to work things out that way, that resistance. The thing to be careful of here, I mean, if you're constructing a circuit, is that this is only true if the inductors are far away from each other. Because they all have magnetic fields, if you have magnetic field from one, it can affect the magnetic field of the other. So in a practical, real-world situation, make sure you put the inductors far enough away from each other that the magnetic fields are not interfering. So example 19, let's take a look. All right, for example 19, we want to know a bunch of things here. So what is the final current? So I max is going to be the EMF over the resistance, and that's the total resistance because this battery has an internal resistance of 1 ohm. So keep that in mind. So this is 6 volts over 4 ohms, and that gives us 1.5 amps. That's the final current. And so now find the instantaneous current at all these different times. So here's B. Since we're going to need the time constant here, we can just find what tau is. So tau is L over R, which is going to turn out to be 0.05 seconds, because it's L over R, so 0.2 over 4. Okay, so for 1, we want to know what is the instantaneous current at 0.01 seconds. And so our equation, this is charging up, you could say. So it's going towards I max. So it's going to be 1.5 amps times 1 minus e to the negative t over 0.05. And so all I'm doing now is I'm plugging in the 0.01 into this. And you should get 0.27 amps. For 2, we want to know at 0.05 seconds. Well, 0.05, that's the time constant. So I know I'm at 63%. So you can just do 63% times 1.5, or you can go through the trouble of putting it all in there. Either way, you should end up with 0.945 amps. For 3, all you're doing is plugging in 0.1 into this as that time, and you should get 1.3 amps. All right. So here's a simple sketch of this thing. So we've got the 0.2 Henry inductor, internal resistance of 3 ohms, so that's with that thing. Connected to a 6-volt battery whose internal resistance is 1 ohm. Like before, draw a simple sketch. And now we want to find the current after the inductor has been short-circuited. So what we're doing is we're putting a short circuit here. So that's what this is, like a switch. And so what's happening is the current, there's already current in here, right, in the circuit. It's at I max, and then it's going down over time, right, because the magnetic field is dissipating, you could say. So now in this case I have a new time constant because I'm no longer taking into account this one. So it's 0.2 over, it's R over L, so 0.2 henries times 3 ohms. It comes out to 0.0, let's say 67 seconds. That's our time constant. And so the current is going to be given by I max times e to the negative t over 0.067 seconds. Right. And I max was this, or I max, yeah, no, sorry, I max was 1.5 from the previous example. And so in part A, well, we already did the simple sketch, but for part B, all we're doing is we're plugging in negative 0.1 into this. So we're plugging in 0.1, and you should get 0.337 amps. And then at 0.2 seconds after, I don't even have the answer here. Again, just plug and chug. All you're doing is putting 0.2 into that to find what the current is at that later time. All right. What's up, man? Hey. Okay, the energy stored in the magnetic field of an inductor. Here's the derivation, right? It's based on EMF and Kirchhoff's law, right? L d I dt plus IR, and then what power is, and then energy is, power is the derivative of energy. And so, anyway, what you end up with is this Li squared over 2. That's it. That's what the stored energy is. And you're going to see just plug and chug type equations here. So the first one, example 21, looks like this. So for part A, the stored energy, writing the wrong thing here. The stored energy in an inductor is 1/2 Li squared. So that's 1/2 of 2 times 10 to the negative 3, 2 millihenries. And then 0.2 squared should give you 4 times 10 to the negative 4th joules. That's it. And then for B, so we're calculating the current. If we just solve for current, then it's 2 times 1 joule over, what's that? Oh yeah, 2 times 10 to the negative 2, which should give you 10 amps. Okay, and that's the last sample problem. And now we're just looking at energy density, right? Energy per volume. And so all this is it's UB, this, divided by the volume of the inductor. And so you've got the different forms of this, and we use a lowercase b for the energy density of an inductor. And that's it for Chapter 30, but there's actually an addendum coming up to Chapter 30, so